if the value of hydraulic conductivity in an aquifer doesn't change depending on which direction you're considering, that's considered an isotropic aquifer. And if not, it's an anisotropic aquifer. So in an isotropic aquifer, K is the same in all directions. And if not, then it's anisotropic. If hydraulic conductivity has the same characteristics as you move around in space, it's considered a homogeneous aquifer. And if it varies in space, if it gets bigger and smaller as you shift laterally in space, it's considered a heterogeneous aquifer. So hydraulic conductivity has the same characteristics everywhere. And again, if not, then it's a heterogeneous aquifer. Let's draw some pictures to make this a little bit clearer. We'll consider 4 different aquifers here. And I'm going to use little arrows to denote the direction and the magnitude of the hydraulic conductivity. And so this we will call K in the y direction, and this we will call K in the x direction. In this case, I'm drawing it such that the magnitude of these arrows is the same both at a location and as you move around in space. So this is an isotropic because it's the same no matter which direction you're pointing, and a homogeneous aquifer. It doesn't change in space. Let's consider another aquifer where K in the x direction is significantly larger than K in the y direction. But if you move in space, it's the same. You see the same pattern. So the length of the x is the same in space and the length of the y is the same in space. In this case, K varies based on direction, but it doesn't vary based on where you are in the aquifer. And so this case here is going to be anisotropic, but still homogeneous or homogeneous. Okay, I think we can see where we're going here. We now are going to have K being the same in both directions. So the direction doesn't matter. But the magnitude in any particular direction is going to shrink as you move in space. So here we've got an isotropic heterogeneous aquifer. And in the final example, our little vectors that denote K are going to be different in direction at a location, but they're also going to be varying in space. So the X vector is changing in size as you move along. And so we have both an anisotropic and a heterogeneous aquifer here. To formalize these definitions a little bit more, in the isotropic case, here, K in the x direction is equal to K in the y direction, and if we're considering 3 dimensions, it's the same in the z direction. In the homogeneous case, K doesn't change as we move in space. So if we look at the partial derivative, dk or del k del x, it's 0. And the same in these other directions too. There's no gradient in the magnitude of K as we move in space in a homogeneous aquifer. And so that's one of the ways that we can formalize mathematically these different properties of how hydraulic conductivity varies or not in space in an aquifer.